That'd be confusing. The Elizabeth chair. Also, you live here. Yeah, I think I'm gonna bring it back. I'm gonna be here with the water.
So you want to look at, why is there this? You want to look at this if you want to know like the updated, because like I also update down here, but I'm not as good at changing these up here down here. But this here's like the very, very official, like the whatever is in the simple syllabus, like I pasted that at the beginning of the semester thinking like that's where I want to be at certain times of the semester, but you know, we're behind. We're fine. So the test 2 is here. So we have a while because there's like this week before spring break and then 1 week after the spring break. So we have that. I also posted the solution. So every time you see this set of banner of links, it's out of 37. So you should like double check, if you got like -5, then your score should be 37 minus 32 out of 37. So if you did that on your calculator, that percent should be your score. It would be probably lower than 95% because 1 point is worth more out of 37 points. And you can see where each of the points came from for like this one, if you like kind of did up to here was +2 and up to here is +2. So each of these were worth like 4 because they were both like 2 + 2s. And then, some of them are just like +1 because this one was supposed to be relatively easy. So like if you see like I missed some stuff or like I took off when you shouldn't have gotten taken off, then you can point that out and I can fix that. And again, you don't have to tell me if I like forgot to take off something. So that's that. And the grade calculator, I usually activate that after the second test because with the points and the fact that I will also weight the final more if you end up doing better on the final and then take weight away from the tests and put it onto the final. So with that, it turns out that pretty much for basically most, if not all of you, you can pretty much get whatever you want in the class so long as you start getting that from now on. So like include if you get that including on the final. So that's why the grade calculator, after the second test, I'll activate that. It's kind of like a programmed spreadsheet that allows you to put numbers in and it'll tell you like what you need to score on the future, like test 3 and the final in order to get a certain grade in the class. And you can play with that. And it does make there is a little bit more meaning of doing that after the second test because depending on how well you did between the first and the second test, you may start getting locked out of certain grades. But right now, I think everybody can still get whatever they still want to get so long as they get that. And the grade calculator would just kind of say the same thing. So I just decided to wait so you guys can focus on just doing as best as you can in the class. Come on. All right. So we were covering a couple last cases for this second order non-homogeneous equations. So we moved into sinusoidal functions where you have some kind of trig function on the right-hand side, like cosine or sine. And the solution form is exactly the same as what you would expect if you did it with first order equations. You have to have both trigonometric functions with some capital A and capital B. Those have to also be different. But unlike the first order equations we had before, you have to check with your homogeneous solution to see if there are any terms that match. And if there are terms that match, you have to multiply by t to the entire particular solution, their initial particular solution. And don't multiply by t like more than necessary, because then you're going to have a form of a solution that actually will not work out. You just multiply enough to make all the terms distinct from the homogeneous solution, but no more than that. So don't just like multiply by t to the 5 and say, okay, I should cover it. You just need to just multiply 1 or 2 times, and that's it. And so if you had a forcing function, this is the one that we ended with, is a polynomial times a sinusoidal, then this term here is a first degree polynomial. So you can't use this right here. You can't use like a cosine of t plus b sine of t. This would have been like the right form if you just had a constant in front of the sine term. But if you have a polynomial, you need a general first degree polynomial that's different. So the one that's in front of the cosine has a naughts and a ones, and the one in front of the sine is b naught and b ones. Just like previously when we had this solution form, the a and the b were potentially distinct. So you have two distinct first order general polynomials that are multiplying these. And we justified this by the fact that if you were to plug this into the left-hand side, you're doing some derivatives. There's a product rule, and every time you take a derivative, there's like one of them, one of the terms that are being multiplied, like the cosine or the sine, we'll just take a derivative of that, we'll flip it to the other trig function. The polynomials will go down by 1 degree. So in general, you'll have like a bunch of terms on the left that are combinations of constants times the trig function or something with a t times a trig function. So that's good because on the right-hand side, you have like a t times a sine of t, and you just have to go through and try to find capital a naught and a1 and b naught and b1 such that you can get rid of all of the cosine terms and just keep the t sine of t term that's going to match with the right-hand side. So that's a good initial. It's still the initial, right? So you got to double check because you don't want to plug in something that's going to lead to a false statement or contradiction. And that's always going to happen if you notice that there's any terms that conflict with the homogeneous. So this one, the homogeneous solution is just going to be r squared plus 4 because that's looking at the left-hand side, and you get these imaginary roots, pure imaginary because alpha is 0. So this is like the real solution for this case where you have complex roots for your characteristics. So you have c1 cosine 2t plus c2 sine of t. This is your homogeneous. And then your particular solution, like we had before, is going to be just, right, this thing that I have typed up here, but I'll write it down. So a naught plus a1t cosine of t plus b naught plus b1t times sine of t. And this is already correct because you don't have any terms that conflict. Just be careful because like this, maybe I'll use, what color do I want to use? Use red. This is a 2t, whereas this is just a t. And this is just a t. So these don't match, right? There are no matching terms between this homogeneous and the particular because those are not the same trig functions. So this is already the correct. No need to multiply by t. This is already the correct xp. Okay. Why don't we look at you know, of course, if you were to actually solve for a naught, a1, b naught, and b1, you'd have to like take this, take the derivative of it, and then take the second derivative of it and plug it into x double prime, and then there's no x prime term, so you'll just plug in the original, like this thing again, into the x term. You'll have like a bunch of terms because the derivative requires the product rule between these two, product rule between these two. The second derivative is going to require product rule between all the stuff that end up popping out of the first derivative. It's going to be like all of these things are going to just keep spawning more terms, and it's going to be a lot of mess. So just if the question asks you to find the correct solution form, then you can just leave it like this with your a naught a1s and b naught and b1s, and that's like the part that is conceptually, you know, what's important for these types of problems, is that you actually have a correct solution form that if you were to hypothetically plug it in and solve and do a bunch of essentially calculus and algebra, you would eventually get the right answer. So let's look at this one. So I guess like I could point out like well, maybe there is a statement later. So I'll do this right here. So we'll come back to this one. Let's come back to that one. So let's look at this one, and then we'll go back and look at the other one. this one is similar to what we just saw. We'll have basically, what did I do? So the one we just had was x double prime plus 4x, so the same left-hand side, equals t sine of t. So this, I'll just copy and paste, and then just, let's see if I can find, no, let's do this, screenshot this. So this is what we had. And then we can look at what I changed about this. So it's like the same exact equation on the left, but the only thing I changed was I ended up adding this 2t right here. So because the left-hand side is exactly the same, you know that the homogeneous solution is the same. So I'll just copy and paste this. So all I've done is made the right-hand side be 2t instead. Oh, no, I didn't mean to do that. Where is this? So copy and paste this. So the homogeneous solution is still the same because it's x double prime plus 4x. So this would be the characteristic equation, all this stuff. But this obviously is not going to be correct. It's because not the same exponential. So this is your homogeneous solution from just like the left-hand side. Now, your particular solution is going to be different from what we had before because this is sine of 2t. So that's why your particular solution will have these 2's as well right here. So it has to be the same particular solution, the same trigonometric function that goes into it. So that's why this is your, so I won't even write it. I'll just say like, this is like your particular solution. I just have it already here, right? So you have this right here. This is going to be your initial particular solution form, is going to be based off of, like, I guess I'll just point out here that this is got a 2 right here. So you have a 2 here and a 2 here. But since it's t is a first degree polynomial, you multiply it by a general first degree polynomial, another general first degree polynomial. They may not in general be the same. So have a naught, a1s, and b naught and b1. Now, compare it with this homogeneous solution. Are there terms that match? So if you look at this, if you took the a naught and distribute it with the cosine of 2t, right? Because this cosine 2t get multiplied to each of these, it resembles exactly this term, right? I'll just say like this. The combination of these two, if you distribute this, will match this. And then you also have this right here, distributed to the sine of 2t, will end up being like this. The reason it looks like this is because if you think about this, this is a naught cosine of 2t. A naught is like some constant that we're trying to find that will end up making this solution satisfy this differential equation. But we know that this one is saying that the first homogeneous solution is some arbitrary constant c1 cosine of 2t. So it's essentially the same form. You have constant times the cosine of 2t, an arbitrary constant times this cosine of 2t, and then here a b naught times sine of t. 2t is like arbitrary constant, some constant times sine of 2t. So you have to multiply everything by t, and so this is why we have this right here, is a t right there, and then that is going to be enough because your t is going to get multiplied to each of these. This one's going to be a naught t cosine of 2t. That's not a problem. This one's going to be a1 t squared. There's no t squareds in here. So just by multiplying this entire thing by t once is enough because there are no terms that will conflict when you do that. So this is the correct XP. It's the screen thing. Okay, so that's the only change I made just by putting this 2, and that was on purpose because I knew that if I had 2 here, then you're going to have these match, because this one, when I didn't have a 2 here, then it was just t's when the homogeneous has 2 t's. So this was fine because cosine of 2t is not the same as cosine of t. So let's look at these. So this one is like an exponential times a cosine function. So I'll just say this is like some exponential times a sinusoidal. And your initial particular solution form, you wouldn't be, it's not unexpected to think that it would be like the same exponential times some trig function. So we've always had like for if it was just cosine of t, then we would have had a cosine of t plus b sine of t. But because we're multiplying by e to the negative t, we're just going to take that whole thing and multiply by e to the negative t. If we were to plug this into the left-hand side, you'll have to do the product rule between e to the negative t and then this thing. Every single time you take a derivative of e to the negative t, you will pop out an e to the negative t. Every single time you take a derivative of this, you'll pop out another trig expression. So cosines will flip to sine, sines flip to cosine. So essentially, it's going to be kind of the same kind of form. Every single time you so the product rule says you take the derivative first times the second, and then you take the derivative second times the first. So if you took the derivative first, you'll have e to the negative t. If you took and then multiplied by this, if you took the derivative second and just copied the first, you'd still have e to the negative t. So every term, no matter what, is going to have e to the negative t in it. So every term on the left, because the derivative of e to the negative t is e to the negative t, and if you just left e to the negative t, it'll be still e to the negative t. Every single term on the left will have e to the negative t, which is good, because on the right-hand side, you have an e to the negative t. And then you're just going to have like cosines and sines being multiplied to it, which is also good because we have a cosine of t on the right-hand side. So all our trying to come up with is an a and b that will, get rid of all the terms except for a 5e to the negative t times cosine of t. So this makes sense that this would be a reasonable thing to plug in to make this to resemble this left-hand side to resemble the right-hand side. Now you have to sit here and so the process is you look at the right-hand side to build your initial solution, particular solution form, but you always have to try to see if there's any potential matches with the homogeneous. So what you're going to do is you'll do the homogeneous. So r squared plus 2r plus 2 is equal to 0. And this, if you, so you'll have to, do the quadratic equation for this. Because it doesn't factor. But if you did that, then you'll end up getting that r is equal to -1 plus or minus I. I'm gonna trust that you guys can solve this quadratic and see that it's gonna become this. So then right, the real part, alpha, is equal to -1, and your imaginary part is equal to just +1. And so you're going to use, what is it, this thing? Just use this again. So your homogeneous solution will end up being C1 e to the negative t, because its alpha is -1, times cosine of t, plus C2 e to the negative t times sine of t, because the beta and so we have, this is our homogeneous solution. Now, if you look at your initial particular solution, which is up here, this one right here, are there terms that will match? Yeah, because if you look at this, if you distribute it, had you distributed this e to the negative t with this, it would have been a e to the negative t times cosine of t, which is like this right here. It's like a constant times, and then you have this one distributed with this one. Well, I'll use red. This one distributed with this one will be b e to the negative t times sine of t, which is going to match this. So you have these terms are matching. So I'll just say like this stuff. And then these are matching. So you'd have to multiply by t, which I'll just highlight that this is what happened here. So we had to multiply by t to the whole thing. So I just took this and then just put a t in the front. And now if you look at this, there's not going to be any terms that match. So it turns out this initial particular solution, every term matched with the homogeneous solution. So if we actually plug this in, you'll just get his false statement. You'll get 0 equals 5e to negative t times cosine of t. Because this exactly solves the homogeneous solution. So multiplying by t now will fix that. And so this is the correct solution form. Okay, so the last case is this. Sorry, it looks so it's like a lot of these things are just like getting just more and more complicated. Essentially, you have polynomials, exponentials, and sinusoidals, and you might have them all by themselves. You might have products of them. But what if you just had like the most general form would be like you have, instead of 2 different things, you have 3 different things multiplied together. So you have this is a degree 3 polynomial. This is an exponential. And we've only had 2 at a time, but now we're looking at sinusoidal as well. So you have 3 of them multiplied together on the right-hand side. The idea is the cosine. Yeah, there's a way you could think about this is like, so had you not had an exponential, if you didn't have an exponential, so let's say hypothetically you didn't have this one, then it was just t cubed times cosine of 3t. Then from before, we know you'll have to split it between cosine of 3t and sine of 3t. And then the general 3rd degree polynomial for the cosine and general 3rd degree polynomial for the sine, and they may be different. So you have a's and then b's. And then we're combining that with the idea of when you had an exponential multiplied, then we just took the exponential and just multiplied to the entire. So cosine is going to become a cosine of t, b sine of t, and then we multiply the negative t to the entire thing. So that's why if we have the e to the negative 2t, it would have been like take all of that and then multiply by e to the negative 2, e to the 2t. So this is here and this is here. So this is like the correct solution form, initial correct solution form. So if there if there are any things that match, then you'll have to multiply by t to this whole thing as well. Why does this make sense is because if you were to do like the derivative, okay, because you're trying to plug this into the left-hand side. You'll have 2 terms here, right? That's fine, but each of them are actually a product of 3 things. You have a product of this polynomial times an exponential times a cosine or some sine. So there's a 3-way product rule, right? Where you like have like, 3 things multiplied together. So you take the derivative first times copy the other 2, plus you take the derivative of the middle one and copy the other 2, plus you take the last one's derivative and copy the first 2. That's a 3-way product rule, right? So this is what it's going to look like. So a 3-way product rule is like saying if you had f g h prime is the same as f g h plus f g h plus f g h, but the prime gets on the f, on the g, and then on the h. So the idea is that you're eventually going to probably have combinations of polynomials times exponential times sinusoidal. Okay, so think about what a sinusoidal derivative would be. It would just be another trig function. So it's going to be like cosine flips to sine flips to cosine. The exponential derivative will just be another same exponential. And then the polynomial derivative will just go down by 1 degree. So you're going to have essentially a bunch of trig functions multiplied by e to the positive 2t times some polynomial that is up to t cubed or as low as up to t. Because if you took a derivative, it would be t squared. And then if you took another derivative, it would go down to t. So you'll have like, it's going to be a mess because there's like, every one of these terms are going to spawn 3 different new terms. But each of those terms will have e to the 2t in it for sure, because the derivative of e to the 2t is to e to the 2t. And if you weren't taking a derivative of e to the 2t, it would still be e to the 2t. Or m multiplied by some cosine of 3t or sine of 3t. times some polynomial that's up to t cubed. Because the x term, for sure, when you plug it in, will just keep the t cubed. And so you'll have all of that on the left. You may have t squareds or t and stuff, but it will just be, all of those terms on the left, which is fine because you need terms like t cubed e to 2t times cosine of 3t to show up on the left. And so there's going to be there's 8 coefficients where you're trying to find them that will leave just t cubed e to the 2t times cosine 3t left, and everything else has to vanish. Okay, so this is a reasonable solution form from that perspective. So you will use that. Now, we can't go lower. So if we had said that, for instance, we wanted to use a polynomial that was like, for instance, let's say we just didn't do a third degree polynomial, we just took this off and it's only up to t squared. The left-hand side will never have a t cubed term if you did that, because derivatives of these things will just reduce the polynomial. It will never make it go higher. Whereas the right-hand side has a t cubed, so then you're going to have an issue because you're never going to get this left-hand side to resemble. So we definitely need the t up to the t cubed. We can't go lower than that. You could go higher, though. You could go like a4t to the fourth and b4t to the fourth, but all of those terms would have b4 would equal to 0 and a4 would equal to 0 anyways if you were trying to match, because there's no t corresponding t to the fourth on the right. So you don't have to go higher than this, but you don't want to go lower than this. And so now you have to just sit and just find out what the homogeneous solution is. So r squared minus 4 is equal to 0. And this one's distinct real, so you're just getting r squared is equal to positive 4. So you're just going to get r is equal to plus or minus 2. And given that, your homogeneous solution will end up being just x of h is equal to distinct, so it's e to the 2t, or you can do negative 2t plus c2 e to the positive 2t. Yes. It doesn't matter. It doesn't actually matter. So this is it, but this is not going to have any problems, right? Because all the terms, if you were to distribute this out, there's like 8 terms up here, but every single one of them has some kind of cosine of 3t or sine of 3t attached to it. It looks like maybe like this e to the 2t right here matches, but it won't, because every single term will have e to the 2t, but they also will have some kind of cosine of 3t or sine of 3t that's attached to it. So that means that it doesn't actually match that. So this is going to be your particular solution form, and there's no need to multiply by any kind of t on this one. Now, if you were to solve for the A naught, B naught, and all that stuff, you'll have at least 8 different conditions from matching terms from the left to the right. And it would be like solving like for 8 unknowns, which is going to be a lot of work. And I mean, even before you get to that point, you'll get a lot of work because you'll have to take the derivative and the second derivative. So this is why it's just asking you the solution form. So let's look at this one. This one is looking at the, so what did I do? Let's compare with what we had up here. So all I did was I kept the same right-hand side, t cubed e to the 2t cosine of 3t. I just switched up the left. So instead of x double prime minus 4x, I had x double prime minus 4x prime plus 13x. So your initial solution form, which is in this green box right here, turned out to be fine in this earlier problem. We'll see if it is for this one. So this is just a copy of and paste, right? So this right here, a naught, a1, a2, a3, t cubed, e to the 2t, cosine of 3t, b naught, b1, all this is exactly the same, because your initial form is just built off of the right-hand side, and both of these right-hand sides are the same. So, of course, you're going to have the same initial form for your solution. But then you have a different left-hand side, so you're going to have to do the homogeneous problem, which is going to be the characteristic equation, r squared minus 4r plus 13 is equal to 0. You're gonna, okay, so this one you can't factor, but you can use quadratic formula and you'll get 2 plus or minus 3i. That you can check on your own. And if you get that, you see your alpha and you see your beta. Alpha is the real part. Your beta is your imaginary part. It's 3. And then we have to just grab this again, which is going to tell you where things go. I mean, you might be very comfortable and memorized this formula now, but we'll keep it here. Where is it? It is. So we have this, and so our homogeneous solution will end up being x of h is equal to c1 e to the 2t, that's your alpha, cosine of 3t plus c2 e to the 2t sine of 3t. That's that. Okay, so now let's look at our first form for a particular solution. Are there terms that are gonna match? You distributed this out, there's 8 terms, and there's this a naught times e2t cosine of 3t. This a naught being some constant. This is like c1, e2t cosine of 3t. So if you look at that, this actually would match if you were to multiply this out. Right, I'll just do this. So the distribution of these two will match with this right here. And then you have this one, this b naught, and this e2t sine of t, if you distributed that out, will resemble this right here because it's like c2 e to the 2t sine of 3t. So you have these terms match. So you need to multiply this entire thing by t, which means that there's a t here as well as a t here. I mean, you could have put a big square bracket in front of like this whole thing and then put a t, but I just went ahead and said if you had done that and distributed the t, there would have been a t here and a t here, and the rest of it's the same. And now every single term has at least t or in it, so, there's t or t squared or t cubed or t to the 4th now that you've introduced this additional factor of t, which is going to be fine because there's just no t's in any of these expressions. So that's your final solution form. This is the correct solution form. This is even worse if you were to try to solve, because now you have a product rule that's like 4 ways, or you could distribute this in, and I guess it's a 3-way product rule still. But this is the form that you'd expect your solution to be. And in practice, you probably never want to actually solve this for real using the method of undetermined coefficients, because it's going to be a really long process. So we'll learn something called Laplace transforms, later in the course. That's better to use for something like this, because that one's going to be not as much work. And actually, it's reasonable enough that you could do it using that technique. But you could use the method of undetermined coefficients, like hypothetically. It's just in practice, nobody would use that for this kind of problem. So we saw superposition before. So I'll just skip to the problem here, right? Had you seen this, like x double prime minus x plus sine of t minus e to the t, you probably know from the past, you'd expect that this looks like you have 2 different forcing functions that are added or subtracted on the right. So it's like a 2-in-1 kind of problem where you do like one particular solution, xp1, which is like coming from the sine of t term. And then there's another xp2 solution that comes from this term. So it's like this will give you like an xp1, and then this will give you an xp2. That used to be what you did for first order equations. Actually, you can also do for second order equations. So this is actually when I actually introduced this superposition principle, it probably came from the 2.6 that we're currently in. So it's saying that if you have a second order equation ax double prime plus bx prime cx is equal to some forcing function f1 and some forcing function f2, you know, and I always use like, this is my orange one and this is my red one. You can solve them separately and you'll get like an xp2 and you'll get like an xp1. And your actual xp, that is the particular solution to this thing, is just the sum of those two. It's the superposition of those two. So you can do that so long as you're so it turns out that you're, you know, so I'll just make it clear here that that's it's a principle that only applies for linear differential equations. These A, B, and C, these A, B, and C's, what does it mean to be well, it's fine. For us, they could also be different, but linear just means that your x double prime x and x are only appearing to a power of 1. But these A, B, and C's actually don't need to be constants to still be linear. We are looking at coefficients that are constants, but we'll look at problems where these coefficients are not constants. So what do I mean by that? Let me just say, so far using all of these techniques that, well, it's only just this one technique, which is the method of undetermined coefficients. We have had differential equations of the form A with these A and B and C all constants. But like, let's say hypothetically you had an equation like t squared x double prime plus e to the t x prime plus 1 over t x is equal to, say, like ln of t over t. This is not going to be something we can solve yet because this has non-constant coefficients. So these t's, this e of t, this t squared, they're not just numbers. Like this is like 1 and -1. And furthermore, we've never had, so this is like kind of an exotic forcing function, I would say, because we've had only right-hand sides that are sinusoidal or exponential or polynomial or some products of those things. We've never had a forcing function on the right that looks like this. And every single differential equation we've had for second order has been constant coefficients. So 13, -4, or, you know, 2 or 2 and, you know, 1 in front of the x double prime. So we've never had like t squared, either t or 1 over t and all that. And so we wouldn't even be able to solve the homogeneous problem for something like this because the characteristic equation wouldn't be what we've gotten in the past, where, you know, like with the chain rule end up being like AR squared plus BR plus C or something like that. And then you can solve for the R that will end up working to force this thing to satisfy. So we don't know how to solve these yet, but we'll get to it. So that's what I mean by constant coefficient and non-constant coefficient. So for this one, let's do the separate problems. Let's do XP1 is like trying to solve this differential equation with your so I'll just say this is like saying we're just trying to solve this with just sine of t on this side. But before we do that, let's do the homogeneous problem. So I'll just move this down and say a homogeneous problem is going to be r squared minus r is equal to 0, which means that you get r times r minus 1 is equal to 0. So therefore your r is equal to 0 and 1. So if your r is equal to 0, wait, no, I made a mistake. This is a 1. So it's going to be r squared is equal to 1. So r is equal to plus or minus 1. Therefore, your homogeneous solution will equal C1 e to the t plus C2 e to the negative t. Yeah, just be careful. This x is not a prime, so it's just going to be a 1 there. And so this is our homogeneous solution. Okay, and let's look at the orange particular solution. Is going to just solve this equation with a sine of t on the right. So then you're just going to have A cosine of t plus b sine of t. Okay. And that's our particular solution for our and why did I do the homogeneous? To just check if I need to multiply by t to this. There's no problems, right, with this one. Now let's look at the red one. The red one is going to be your xp2, and it's going to be basically solving the same differential equation with just the negative e to the t on this side. This one, your xp2, will be built off of the right-hand side. So you have some exponential like this. So I'll just use a naught e to the t. I'm using a naught because in general, this a and this a won't be the same. So I'll just use a naught for this one. Now, does this have any issues compared to the homogeneous? Yes, it does. So you'll have to multiply because you see these match. So this one and this match. So we're going to multiply this one by t. So your xp2, your correct xp2 will be a naught t e to the t. Okay. Now notice that I don't multiply this one by t. I only multiply the sub-solution, the particular sub-solution that has the issue. So just be careful with that. You just only multiply. So some people, I think even with first order superposition, they might have said, well, if I look at this right-hand side, you might be just like, okay, well, it's going to be like a cosine of t plus b sine of t plus a naught e to the t. So you might say that, but and then and that's fine. But in the past, you know, you didn't have to multiply by t, so you know this was not something you had in the past. But like in this case, the t only gets multiplied here. So I'll just put a little thing here and say this one only gets multiplied by t. This one stays. So it's only the subsolution. So when using superposition, remember to make the guesses for xp1, xp2 separately. Then if one of these particular substitutions has conflicts with terms of homogeneous solution, multiply only that one and not the other ones. So that's why only this one got multiplied by t. So that's the solution form. So what we're going to do now is just solve. So you're just going to say, you know, your x double prime minus x is equal to sine of t. So we said, what is it? This is our particular solution form. So what we plug this in, right? So we're going to plug this in. But before we plug it in, let's just take the derivative. So xp1 prime is equal to negative a sine of t plus b cosine of t. Xp double prime is going to equal negative a cosine of t minus b sine of t. And then we plug this in. So we're going to plug this in. X double prime is this one. And then you're going to minus this by the entirety of this guy. And this is supposed to equal sine of t. So let's just, you have an a cosine of t minus an a cosine of t and a minus b and a minus b. So there's like two of these, and then it's going to be a cosine of t. Well, we'll just write it out. We'll just say 2a cosine of t minus 2b sine of t is equal to sine of t. And then the idea is like you just say that I want this to go away and then these two to match. So that means that a has to be 0 because this has to vanish. And then you have that b has to be, so negative 2b has to equal 1. So therefore your b has to equal negative half. So that one's that. And then this one is the a. And that one's good. We're done with that one. let's look at the other one, which is this differential equation with just the e to the t on this side. So it's going to be x double prime minus x is equal to negative e to the t, negative e to t because there's a minus e to the t there. And this one we said the particular solution form is this with a t that's there. So I'll just copy that. Let's just delete this, delete this. I'll make all this red because this is like for the other solution. Okay, so now we just have to take the derivative. So I'll just say the product, this one's a more painful derivative, but if you did the product rule, you'll end up getting a naught t plus 1 e to the t, and then xp2 double prime would end up being a naught t plus 2 e to the t. Okay, those are your derivatives. So then when we plug it in, you have xp double prime, which is this one, plus or minus this one is equal to negative e to the t. You can just divide everything by the t, so this goes away and becomes negative 1 on this side, this and this goes away, and then you can just say that this is going to equal, if you distribute this, it'll be a naught t plus 2a naught minus an a naught t, because this is just a naught t, is equal to negative 1, because this is just negative 1. And of course, these two are the same. A naught t and minus a naught t are the same. So you're left with a naught, 2a naught. Well, 2a naught. Let's do this. 2a naught is equal to negative 1. Therefore, your a naught is equal to negative half. And that's your a naught. So what is the final solution? After superposition, this is like I have my xp1 is going to equal, because a naught is 0, this is 0, b is negative half, so it's going to be negative half sine of t. That's my xp1. And then we add to this the other solution, which is minus 2, 1/2, I mean, t e to the t. This is my xp2. And then we add to this your homogeneous solution, which we must have computed. Here it is. It's up here. It's a homogeneous. That's your superposition that you've seen already before, but now it's for second order equations. This is your homogeneous. So this is your general solution. Okay. So this particular problem also says, use these initial conditions. So we'll just kind of do that next time. But the initial conditions just means plug this initial condition into this and you get your C1 and C2. So you need 2 conditions for 2 unknowns here. And so that's why they give you this one and this one. And that's kind of it for this section. We'll move on to applications, which is like vibrations and oscillations. But I'll also go back and probably like there was something I skipped, I think, up here. This one right here, I'll quickly talk about that too. But I think this is like most of what I needed for setting us up before applications. I have office hours right now. If people, it's actually in this room, so if you want to stay. But have a good weekend.